Today, we're going to crack open one of the greatest scientific case files of all time. We're going on the hunt for the true nature of matter. And trust me, this isn't just a history lesson, it's a full-blown detective story, full of clues, twists, and shocking revelations that literally changed our understanding of, well, everything.
So let's just start with the biggest question there is. Think about it. What are you made of? What about the chair you're sitting on, or the air you're breathing? What is all this stuff, really?
For thousands of years, this question was a total mystery, one of the biggest cold cases in science. So in this explainer, we're going to follow the trail of clues, piece by piece, as uncovered by some of history's most brilliant scientific minds. So let's start at the beginning of the investigation.
Our story kicks off with an idea so powerful, so convincing, that it's stuck around for more than 2,000 years. The theory that everything was made of tiny, unbreakable little particles. This all goes back to the ancient Greek philosopher Democritus. He came up with the term atomos, which literally means uncuttable. His logic was pretty simple. If you take something, say a piece of paper, and keep cutting it in half and in half again, you'd eventually get to a point where you just couldn't cut it anymore. That final, fundamental bit, that was the atom.
Now, for centuries, that was just a cool thought experiment. But then we fast forward to 1803, and a scientist named John Dalton takes this idea and turns it into a real, honest-to-goodness scientific theory. He pictured atoms as these tiny, solid, indivisible billiard balls. And this was a huge deal. Why? Because his model could actually explain why chemicals combined in the ways they did. For almost 100 years, this was the accepted truth. Case closed. Or so they thought.
But you know how it goes in any good detective story. Just when everyone thinks the mystery is solved, a new clue emerges that doesn't fit. A clue that blows the entire case wide open.
And this is where the pace really picks up, right at the tail end of the 1800s. Our first key detective in this part of the story is J.J. Thomson, and in 1897, he's about to find something that will completely shatter that old billiard ball model of the atom. So what was his smoking gun? It was this strange device called a cathode ray tube. It's basically a sealed glass tube with almost all the air sucked out. You've got a negative plate on one end and a positive plate on the other. And when scientists zapped it with a high voltage, these mysterious, invisible rays would shoot across the tube. Thomson was obsessed with figuring out what in the world they were. Okay, so here are the clues he gathered. First, the rays traveled in a straight line. But here's the kicker, the big clue. He found he could bend the rays with a magnet. Even more telling, if he put electrically charged plates near them, the rays would bend away from the negative plate and towards the positive one. So what does that tell you? Exactly, opposites attract. The rays had to be made of tiny particles with a negative charge. And since these particles were coming from the atoms inside the tube, that could only mean one thing. Atoms themselves had smaller, negative parts inside them. Bam! Just like that, the 2,000-year-old idea of an indivisible atom was toast. Thomson had discovered the first subatomic particle, the electron. But of course, solving one mystery just created a new one. We all know that atoms are neutral, right? They don't have an overall charge. So if they've got these negative electrons inside, there must be something positive in there too to balance it all out. The question was, where was it?
Thomson took the first stab at a new model. It got nicknamed the plum pudding model. Just picture a ball of positively charged, pudding, with the tiny negative electrons stuck in it like raisins or plums. You could also think of it as a blueberry muffin, with the muffin being positive and the blueberries being the electrons. It was a logical first guess, but our investigation is far from over.
Because in science, a guess is just a guess until you test it. And this plum pudding model was about to face one of the most important tests in history, an experiment that would lead to a discovery even more shocking than the first.
Enter our next detective, Ernest Rutherford. In 1911, he set up this amazing experiment. His team fired a stream of tiny, positively charged particles. He called them alpha particles, kind of like microscopic bullets, at an incredibly thin sheet of gold foil. Now, if the plum pudding model was right, those bullets should have zipped right through the soft pudding. And, most of them did, but some of them got deflected. And incredibly, a tiny few, like 1 in 20,000, bounced straight back. Rutherford later said it was as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. It was just impossible. This completely bonkers result could only lead to one mind-bending conclusion. The fact that most of the particles went straight through meant the atom wasn't some solid pudding at all. It had to be almost entirely empty space. So, what about those few particles that bounce back? The only way to explain it was that all the positive charge and nearly all the atom's mass was packed into an unbelievably tiny dense point right at the center. He called it the nucleus. Most of the alpha particles missed it completely, but the few that came close were repelled by its strong positive charge, and the very few that scored a direct hit, they bounced straight back.
Okay, so the picture is getting a lot clearer now. We've got these tiny negative electrons zipping around a tiny positive nucleus. We're getting close, but the picture still isn't quite complete. There are still a couple of loose ends we need to tie up before we can finally close this case.
The first loose end was, what exactly is that positive particle in the nucleus? Building on some earlier work, Rutherford's team was able to confirm that the nucleus contained positive particles, and they figured out that the simplest version, the one in a hydrogen atom, was the basic unit of positive charge. They gave it a name, the proton.
But just when they thought they had it all figured out, the math wasn't adding up. When scientists actually measured the mass of different atoms, they were always heavier than just their protons and electrons put together. A helium atom, for example, has 2 protons, but its mass is about 4 times bigger than a proton. There had to be something else in the nucleus, something with mass but no charge. Something was missing. The final piece of this epic puzzle fell into place in 1932. A physicist named James Chadwick was doing experiments where he fired those alpha particles at a sheet of beryllium. And when he did, a weird new kind of radiation came out. It had no charge, but it was powerful enough to knock protons clean out of other materials. This was it, the final clue. By measuring the energy of those protons that got knocked out, Chadwick figured out that this mystery radiation was actually a stream of particles that had about the same mass as a proton, but with 0 electrical charge. He had found the missing piece. He called it the neutron. And with that, the case was finally closed.
So here you have it, the complete case file. After a decades-long investigation, the atom was revealed to be made of 3 fundamental particles. The negative electron, our first clue, discovered by J.J. Thomson. The positive proton, found hiding in the nucleus by Rutherford. And the elusive neutral neutron, finally tracked down by James Chadwick. This is the atom as we know it today. So the biggest takeaway from this whole detective story is that the solid world you see around you, it's basically an illusion. Every single thing, including you, is made of atoms that are almost entirely empty space. Which leaves us with one last fantastic question to chew on. If that's true, why can't you just walk through a wall? But that is a case for another time. Thanks for joining the investigation.